Hello, welcome back. We're going to be working with energy balances with chemical reactions. The enthalpy of formation is the amount of enthalpy or heat, it was called heat previously, required to form a compound from these elements. So the elements are for pure elements such as hydrogen, oxygen, nitrogen, or chlorine, it's zero. This is the reference. And from here, you are going to be seeing how much energy you need or require in order to form this, this compound. So in the selected physical property data, you can find this column with this enthalpy of formation. It is in gaseous phase or liquid phase, right? And this is in kilojoule per mole. And this is at the standard conditions, which means 1 atmosphere and 25 degrees Celsius. In order to determine this enthalpy of reaction, we can determine this with this enthalpy of formation, right? Such that in the reaction, the enthalpy of reaction is going to be equal to the sum of the products times the stoichiometric coefficients minus the reactants times the stoichiometric coefficients. If this is positive, it means that this requires energy, which means that it is endothermic. But if it is negative, it is going to generate or take out this energy, which means that it's going to be exothermic reaction. If we have different temperatures, what we can do, instead of doing the enthalpy of reaction at different temperatures, we can do this, this route or this thermodynamic pad. We can state the reactants at this temperature, then with the integral of Cp dt, which we have already seen, we can go from Ti, or the initial temperature, to the 25 degrees Celsius, do the enthalpy of reactions at 25 degrees Celsius, and then get from 25 the products to the final temperature. This is because it is easier to do that than to having a lot of delta H of formations at different temperatures. So this is the thermodynamic pad. And remember, since this is a state function, the enthalpy, you only are looking for the delta H, no matter which path you get, okay? There is another situation or another enthalpy or heat of combustion that was previously reported, and it's also useful. And this is when a compound is oxidized with oxygen to produce CO2, water, etc., 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 right? It's still at 25 degrees Celsius and 1 atmosphere. And the reference are now compounds such as CO2, H2O, or oxygen. And here you are going to be doing the enthalpies of combustion of the reactants minus the enthalpies of the products times the stoichiometric coefficients, right? So this is going to fit the heat of reactions calculated with the enthalpy of combustion. And the enthalpy of combustion is the last column of this table. So here you can see these are negatives, which means this is because the products at the very end are going to be zero, okay? With this, you can calculate what we call the heating values. And the heating value is when you have, let's say, air in a combustion chamber, the fuel, and you're going to be generating heat, right? Very common when you're burning fuels. And you can have the products in vapor water or liquid water. If you have it in liquid water, that's the high heating value. But if you have the low heating value, let's say, is going to be when this is vapor. So actually you can get from the low heating value is equal to the high heating value minus the enthalpy times the mass, of course, of water, of vaporization of water, because you are just going or sending the liquid to vapor, okay? Here is an example of how to calculate these heating values. So this is the combustion of octane, N-octane, which is the main component of the gasoline of our combustion engine cars in the cars, right? So this is the oxidation, and you can look for the delta H of combustion in the table for N-octane. So the high heating value is going to be equal to minus the this heat of combustion, and since we are usually working these heating values in not mole but kilogram, we are going to do this over the molar mass of this N-octane. So this is going to be negative, but negative times negative is going to be positive over 114.22, which is the molar mass, yields to this amount of kilojoules per gram, generating at the very end 48,259 kilojoules per kilogram. And usually this is how it's reported, the high heating value once again. The low heating value is just stating this high heating value minus the mass that is going to be produced in this reaction of water, the mass of water that is going to be produced in the reaction, times the delta V of vaporization, the delta H of vaporization, sorry, over the molar mass of water to send it once again to grams or kilograms instead of mole. The mass that you're going to be producing is dealing with the stoichiometric coefficients. So if you're burning, let's say, 1 mole of C8H18, which is octane, then you're going to be producing 18/2 times the molar mass of water over the molar mass of the fuel. So this is the amount of mass that you're going to be producing of water, right, per mole of C2 of the hydrocarbon or of the octane in this case, right? This is the delta H of vaporization for water over the molar mass 18, and this value is going to yield to 3.676 kilojoule per gram, which when you subtract this minus this yields to 44.592 kilojoule per gram or 44,593 kilojoule per kilogram. So this is the low heating value. And remember, once again, the high heating value is when the product is liquid of water, but if it is in vapor, you need less enthalpy, which means that this is going to be lower, right? So the high heating value is this, once again, 48 megajoule per kilogram, let's say, and 44 megajoule per kilogram is the low heating value. And one concept that we're also going to be working with is the adiabatic flame temperature. And this is a temperature that is occurring in the reactor when this fuel is burned and a considerable amount of energy is released. That's the reason why we are actually burning fuels, to release heat, and this heat is going to be used to produce some work. Some of this energy is transferred as heat through the wall, through the reactor walls, and the remainder raises the temperature of the reaction products. The less heat transfer, the higher the product temperature. The highest achievable temperature is reached if the reactor is adiabatic. It means that there is no heat transfer through the walls, and all of the energy released by the combustion goes to raise the temperature of the combustion products. So the maximum temperature that the combustion can actually reach is this adiabatic flame temperature. It means that there is no heat exchange with the surroundings, right? So that is how we're going to be taking into account the chemical reactions. Remember that you can do your material balances through a lot of methods. We were looking previously, such as the extent of reaction or as the atomic species, right? And once you have the material balance, then you can do all your thermodynamic paths with the use of delta H of formation, the enthalpies of formation, or the enthalpies of combustion. Thank you very much. So see you later.